In today's video, we are going to explore the concept of reversible reactions and understand the meaning behind the terms equilibrium and the position of equilibrium. Most chemical reactions are typically represented by a single arrow pointing to the right, indicating that the reactants are being converted into products in a one-way process. Once the products, such as carbon dioxide, are formed in such reactions, they do not revert back into the original reactants like carbon and oxygen. This makes these types of reactions non-reversible. However, in some reactions, you will notice a double arrow between the reactants and products. This indicates that the reaction is reversible, meaning it can proceed in both directions. For instance, ammonium chloride can decompose into ammonia and hydrogen chloride in what we call the forward reaction. At the same time, these two products, ammonia and hydrogen chloride, can combine again to form ammonium chloride, which is the backward reaction. Since both directions are possible under the same conditions, we classify it as a reversible reaction. It is important to understand that the forward and backward reactions do not necessarily occur at the same rate throughout. At the start, there is a large amount of ammonium chloride and none of the products, so the forward reaction happens rapidly. However, the backward reaction has not yet begun since there are no products available. As the forward reaction continues and more ammonia and hydrogen chloride are produced, their concentrations increase, allowing the backward reaction to begin and gradually accelerate. Meanwhile, the forward reaction slows down as the reactant concentration decreases. Eventually, both reactions occur at the same rate, reaching a point where the concentrations of reactants and products no longer change. This state is known as equilibrium. To clarify, when a reaction reaches equilibrium, both the forward and backward reactions are still taking place, but because they happen at equal rates, there is no net change in the amounts of reactants or products. The molecules continue to break apart and recombine, but since this occurs equally in both directions, the overall concentrations stay constant. It is crucial to understand that constant concentrations do not mean equal concentrations. There may be a large amount of ammonium chloride and only a small amount of ammonia and hydrogen chloride, or vice versa. The reaction is still at equilibrium in either case, as long as the rates of the forward and backward reactions are equal. What does change, however, is the position of equilibrium, which refers to whether the equilibrium is more toward the products or more toward the reactants. If the concentration of products is higher, we say the equilibrium lies to the right. Conversely, if there are more reactants and fewer products, the equilibrium is said to lie to the left. The position of equilibrium is influenced by conditions such as temperature and pressure. For instance, heating the reaction can drive it in the direction that absorbs heat, typically the endothermic direction, moving the equilibrium to the right. Cooling the system can shift the equilibrium to the left, favoring the exothermic direction and resulting in more reactants. It is also essential to remember that equilibrium can only be established in a closed system, which means that the reaction must take place in a sealed environment where neither the reactants nor the products can escape. If any substances escape, the system will not be able to maintain equilibrium. Finally, we must understand that every reversible reaction is exothermic in one direction and endothermic in the other. A clear example of this is the thermal decomposition of hydrated copper sulfate. The forward reaction, which transforms hydrated copper sulfate into anhydrous copper sulfate and water, is endothermic. This means it requires heat energy to proceed. The blue crystals of hydrated copper sulfate turn into a white powder of anhydrous copper sulfate as water evaporates. If we then remove the heat and add water back to the white powder, the backward reaction takes place. This reaction is exothermic and results in the reformation of blue hydrated copper sulfate, releasing the same heat energy that was absorbed during the forward process. To summarize, reversible reactions are represented by a double arrow and can proceed in both directions, forward and backward. One direction will always be exothermic and the other endothermic. When the forward and backward reaction rates are equal, the system is said to be at equilibrium, and the concentrations of reactants and products remain unchanged. The position of equilibrium may lie to the left or right depending on the conditions, such as temperature or pressure, and this equilibrium can only be established in a closed system where no substances are lost. That brings us to the end of this lesson. We hope you found it helpful, and if you did, please do like and subscribe. We will see you in the next video.